So the last module we discussed about a problem where we had a small device that is dissipating about 0.21 watts and its thickness is about 200 microns, and it's a silicon device and has a cross-sectional area of 7 millimeters by 7 millimeters, and we wanted to see what would be the junction temperature for it, and the maximum junction temperature is expected to be much less, should be expected to be less than or equal to 100 degrees Celsius. That is, it cannot exceed that 100 degrees Celsius. In the problem number 2, in the problem statement, the team decides to put some molding material and see if that improves the problem. It is an interesting case where we need to look into a molding material that is available only at very low thermal conductivities, which is 0.3 watt per meter Kelvin, and they are able to put a molding material up to a thickness of 1.2 mm. But the overall cross-sectional area of the device has increased from 7 mm to 14 mm. So looking at this, always looking at the thermal conductivity, one may feel that adding this molding material actually may hurt the problem, but indeed in this case, because the dominant part of the, we'll look at the resistance stack, and the dominance alleviating the heat dissipation by providing a larger surface area on the top helps to reduce the temperature. But when you add a molding material, now one has to account for the so-called spreading resistance, and we will assume that there is no contact resistance between the molding material and the silicon, because it's typically the contact resistance for such a situation is quite small. And so we need to account for spreading resistance, that is an additional resistance compared to the case number 1. And so first let's take the problem statement number A as we shown here, and since the heat dissipation is happening only by natural convection, solving for problem A, the resistance network is very simple. There is a conduction resistance because heat dissipation is happening at the bottom. There is a conduction resistance through the silicon. Then there is a resistance to convection, the natural convective resistance from here. The ambient is at 30 degrees C, and we are given that 100 degrees C is the maximum. So we need to see if using this we need to calculate a T junction, because we know the power that is to be dissipated is 0.21 watts at this junction. So we will calculate what is the, we'll estimate a junction temperature and see if it is higher than 100 degrees C or lower than 100 degrees C. For this, because only heat flux is specified, we are not given a junction temperature. Junction temperature is our, we are seeking the junction temperature. So only heat flux is specified. So what we'll do is that we use of a correlation based on heat flux, natural convection correlation. So the Nusselt number from a textbook by Bejan, we have a correlation of the form this. Let me write this and then talk. It is 0.6 times Rayleigh modified because we need to account for flux, not temperature driving forces. So the Rayleigh modified is defined as g times, g is the acceleration gravity, beta is the coefficient of thermal expansion, the flux dissipated times the characteristic length scale raised to the power 4 divided by k times alpha. K is the thermal conductivity of the fluid, in this case it is air, alpha is the thermal diffusivity of the fluid, and the kinematic viscosity of the fluid. If you go calculate the flux dissipated by this device for the area of across 7 mm by 7 mm area, it turns out to be 4285.7 watts per meter square. So, based on this, if you calculate Rayleigh number, that is based on the modified definition, that turns out to be 35,123 using properties of air. So, using this Rayleigh number in the Nusselt number correlation, then we calculate a Nusselt number of 8.2. From this, we can calculate the heat transfer coefficient, and that turns out to be 30.5 watt per meter square Kelvin. With this, now we are in a position to calculate the resistance due to natural convection, and that resistance happens to be 668.9 degree C per watt. So, the way we calculate resistance is using 1 by H times surface area. H is something we just estimated, we know the surface area. From these two things, we should be able to calculate natural convection resistance. And using this, ignoring the resistance due to conduction at the silicon, because it is very small thickness of 200 microns, if I write Tj, if I calculate Tj for an ambient temperature of 30 degree C, we get junction temperature of 170.5 degree Celsius. Now, let us look at the problem number B. The area has now changed from 7 mm by 7 mm to 14 mm by 14 mm. So, the surface area has increased, and the current surface area is this. And how do we calculate flux? Should we be calculating based on the source area, or should we be calculating based on the mold area? Because the heat transfer is happening at the mold interface, so we should use the mold area to calculate the flux, and the flux turns out to be divided by this point is that now the flux has reduced to this, that is 1071 watts per meter square. So, if I go estimate a Rayleigh number, now it turns out to be 140492, and the Nusselt number corresponding to this is the Rayleigh modified. The Nusselt number corresponding to this is 11.6. From this, we can calculate the heat transfer coefficient, that is 21.6 watt per meter square Kelvin. So, one important thing to notice is that the heat transfer coefficient has dropped from the no mold case, which was 30.5 to 21.6. The heat transfer coefficient has dropped, but we have much more increase in the surface area. So, if you go calculate the natural convection resistance, it is about 236.5 degree C per watt. But we cannot ignore the resistance, conduction resistance in the bulk, that is through the mold, because it has 1.2 millimeter thick mold, or the overall stack is 1.2, of which 200 micron comes from the silicon. So, using the conduction resistance in the base, which is L divided by Ka, you can add the resistance in silicon plus L by Ka in mold. So, assuming as a worst case scenario that all the major resistance is only from the mold, and if you calculate based on the area of cross section of the mold, which is 14 mm by 14 mm. The conduction resistance turns out to be 17 degrees C per watt. But one important thing to notice is that if I draw a cross section of this is my device, assuming it's insulated, and only 0.21 watt is dissipated here from this base. Heat needs to spread to these locations. So, there is a spreading resistance associated with this problem, and that resistance need to be accounted for. So, there is an area change from 7 mm by 7 mm to 14 mm by 14 mm. Because of this area change, one has to account for the spreading resistance, and using a well known formula for spreading resistance, one gets so the spreading resistance formula that we use is 1 divided by square root of pi times d times k of the solid. So, d is the diameter or the characteristic length scale of the smaller of the heats of the areas. In this case, it will be the 7 mm, and Ks is the thermal conductivity of the mold. So, using that, and if you calculate the spreading resistance, it is 134.3 degrees C per watt. This is only an approximate relationship. This holds only for spreading resistance in an infinite medium, but we use this as a simple approximation for spreading resistance. So, if I add all the resistances for this case of mold, resistance total for mold, which is nothing but R natural convection from the top plus R conduction at the base plus R spreading resistance. Then I have a total resistance of 387.8 degrees C per watt. So, if I go calculate a T junction, then it is about 101.4 degrees C with an ambient temperature of 30 degrees C. Yes, the answer says that even with the mold, the temperature has reduced, but it is not sufficient to be below 100 degrees Celsius. So, one has to improve either the thermal conductivity of the mold, or one has to increase the area further. But nevertheless, this example shows that providing a larger surface area helps to improve the overall heat dissipation, even if you are putting certain molding material which is low thermal conducting. So, this concludes this problem, so that we cannot ignore spreading resistance, and also we cannot say that heat dissipation at a smaller source level will always help. It is always important to spread the heat to a much larger area and then dissipate, because the dominant resistance is coming from the convective side. The convection in this case is the natural convection, and the natural convection resistance is much higher than the any other part of this. So, that increasing the surface area by providing even a low conducting mold is sufficient to bring the temperature down significantly. So, as an outcome from this problem, when the mold thermal conductivity is increased from 0.3 to 0.6 watt per meter Kelvin, which we won't solve here, is sufficient to bring the temperature, junction temperature for the same area ratios. It is sufficient to bring the temperature well below 100 degrees C. We will go to another problem, problem number 4, and it also again talks about a very similar situation. Instead of natural convection, now we look into a forced convection type situation. And in this case, now we are going to talk about the popular topic of microchannel cooling. And the goal of the problem again seeks two types of solution. There is a silicon device there are two teams. One team says putting microchannels on the silicon itself is sufficient. So this is a silicon device and there are microchannels. Another device, another team, this is team A, let's call it team A. Another team B says no, spreading resistance is important for this case because this silicon is dissipating 600 watts. And this silicon device has an area of 30 mm. By 30 mm. So that's the area, and so team B says we need to spread the heat to a larger area and then we need to put this down. So what they are suggesting is that they take a heat spreader, is the same silicon device that is dissipating 600 watts, but instead now it is spread on much larger area, and then they put down their microchannels on this. So this heat spreader is made of copper, and if we draw a 2D cross section of this, is that now you have a silicon and there are some microchannels laid on this. So this is the junction temperature, T junction, and the liquid water comes in at some 47 degrees Celsius to recover waste heat from this, assuming 100% fin efficiency in the thing. And if we say that the water temperature cannot be more than 57 degrees Celsius, the goal is to figure out that what is the junction temperature if the heat transfer coefficient for both the cases is 8000 watt per meter square Kelvin. So heat transfer coefficient when you enable the microchannels on the silicon is also 8000, and if you enable it on a copper but on a wider base, this wider base is nothing but the heat spreader area is 75 mm by 60 mm. And this copper has a, we have to first draw the network here. So this is the junction temperature, and now we have a heat spreader or a copper, and there is a interface, thermal interface material as well. And microchannels are enabled on top of this copper. So here the water flowing on the silicon directly carries the heat away. Here the water flowing on the copper has to make the copper is in contact with silicon device, and there is a thermal interface material to provide to reduce contact resistance between. So, here there are two additional resistances compared to case number 1. T junction, this is R silicon, this is R tin, and this is R copper microchannel. Here the resistance network is very simple: T junction, R silicon, and T in. The question is this sufficient, or is this sufficient? Will team A win or team B win is the question. So let's look at the problem. So what is that we are given? For the silicon case, let's look at the calculation for the silicon case. So for calculating a resistance for the microchannel heat sinks, we used based on the silicon is we need to use the expression 1 by mCp into effectiveness. Effectiveness, this is the mass flow rate, Cp is the specific heat capacity, epsilon is the effectiveness of the heat sink. Effectiveness is given by nothing but, since this is a single stream heat exchanger, is nothing but HA surface area divided by m dot Cp. M dot, that is the mass flow rate, is given by, is specified already in the problem, and that is about this. The heat transfer coefficient is also specified, and that's about 8000 watt per meter square Kelvin. And the microchannels have a surface area of each microchannel is about 0.5 by 0.5, and overall the thickness of the fins, this is the cross section, this is the for a single channel, and the fin thickness is given as 0.5 mm. So the overall pitch is 1 mm. From this we can estimate, because we know the overall width which is 30 mm, from this we can estimate the number of microchannels we can integrate into this device, and with that we can calculate the surface area. Using that calculation, and we know that we are flowing water through this microchannel device, and the specific heat capacity of water is 4178 joule per kilogram Kelvin, and substituting all these numbers into calculating an effectiveness, and T junction R resistance is about 0.1 degree C per watt, and this is nothing but T junction minus T inlet divided by Q. We know Q is 600 watts, that is given. So from this we can calculate T junction, and that turns out to be 106.5 degrees Celsius for this case. We will look at team B's solution in the next module, so that we can compare team A's junction temperature with team B's junction temperature.